with the quantum annealing today. So compared to general quantum computing, quantum annealing has a large application, and also there are lots of things to say, but I'm gonna just talk about only part of quantum annealing here. So, and also I'm going to focus on the computational part of quantum annealing. So what is quantum annealing? So what is annealing here? Annealing is something you make, you apply to the metal. So when you want to make metal stronger or harder, then you heat up the metal and then put it under water and then do it again. Repeat the process. You make a metal harder. So what is quantum annealing? Well, actually, we're not doing that. We're not heating up the quantum material, but we're doing similar thing. So why does metal gets harder when you do that process, annealing process? Because the metal atoms are aligned in a certain direction. So they're making a stable configuration in itself, right? So stable means that your energy level is lower, right? So kind of similar thing happens in the quantum annealing. So the process of making quantum states to be stabilized is called quantum tunneling. So I'm not saying what I actually understand. I don't understand what quantum tunneling is, but just saying that this is the principle of what happens in the quantum annealing. So what is quantum tunneling? And this is not a good picture because this is not really what happens, but let's see, this is your time and this is your energy level, or it really has no meaning of energy when you talk about the quantum level. But so usually people say when you do the annealing process, it's a continuous process. So as time goes by, your energy level is dropping into a stable point. So when you get to this point, you need a little bit kind of excitement to make into a different level. So that's why you're heating up the metal. So you're at the metal. Let's say your metal is at the energy level this much, and then you're not gonna get to the next level until you heat up the metal into this excited state, and then move along this heap here. But what is quantum annealing? So quantum annealing is when you do some kind of process, annealing process, then the energy level of quantum state just jumps into the next low level here. So whatever you do, you always get the minimum value here, but you're not gonna get the continuous process. It simply jumps from here to here. So the question is, okay, so when you do the annealing, you never know whether this final product is the minimum energy state for all configuration. Same as for quantum annealing. When you could do quantum annealing, after quantum annihilation, you have some quantum state, and you know that it must be local minimum, but you don't know whether it's a global minimum. So basic principle of quantum annealing is you do it several times until you get low enough solution so that you can simply put that solution into the function or the actual value that you want to compute, and then see whether that's the minimum or not. So when you search for quantum annealer or quantum annealing quantum computer, there are several the real quantum annealing computer, and you can actually get access to that computer by paying a small amount of money. Comparatively, so when you log into Amazon Bracket, you can use the quantum annealer, and also you can, I think, the most famous one that makes quantum annealer is the D-Wave, and I'm not sure about right now, but when I tried like a few months ago, D-Wave doesn't allow me to access their computer from Korea, but you can do it with Amazon Bracket, and I think they use the same D-Wave quantum computer. But anyway, if you search for what kind of how the quantum computer looks like, in the D-wave quantum annealer, you might see this kind of picture. So there are flat square box, and there are something going on. You can see what's going on. There are lots of circuits inside, and maybe there's some hairy thing going on, sticking out here. So they say this is a quantum TPU or QPU or quantum annealer brain, and this looks like a little bit different from usual quantum computer that you might see from the IBM's website or other. The reason why is the quantum annealer uses binary variable, which means that every variable is either 0 or 1. So it sounds weird, but because, okay, so this is the bit, not qubit, but that's how it is. I mean, the quantum annealer takes the input of binary values and then outputs the binary values. And something going inside is quantum thing, that kind of having a quantum state, but frankly speaking, I don't know what's inside, what's happening inside. I'm just giving you the computational procedure of this quantum annealer. And also, they use this quadratic polynomial of binary variables. So, as I said, you want to find the local minimum or local maximum in a certain case of some function, and this function must be polynomial, of course, and polynomial of binary variables. Okay? So it's not continuous variable, always 0 and 1. And also this polynomial has to be quadratic, which means the degree is 2. So looking back to our picture, you can imagine that this row and column represent the variables. So for example, x0, x1, and so on. x0, x1, and so on. So if you have n number of these columns and rows, that means this computer, this annealer, can handle at most n variables and binary variables. So I'll tell you what happens in detail, but briefly speaking, so you want to set up your quadratic polynomial. You want to transfer the information of your quadratic polynomial that you want to take a minimized, that you want to find the minimum value of this polynomial into this QPU, quantum processor. And then when you take a quantum tunneling effect by some other thing going on, what happens is after that happens, you measure these values, and that turns out to be the solution of this problem, which means that all the values from x0 to xn minus 1 gives the local minimum value of the quadratic polynomial. So if you have time, go search for MS and bracket documentation, and they'll tell you, it tells you how to use the quantum annealer in their code, and all you need to do is set up the quadratic binary polynomial, and then just put some function and feed them into a function, their built-in function inside their built-in package, and then just go run, and then they will tell you what the solution is. So I want to introduce the important concept called kubo. So what is kubo? So kubo is an abbreviation of quadratic unconstrained binary optimization. So if you want to use the quantum annealer, you have to make your problem into kubo problem. So quadratic means that so before we start from the optimization, before we start with this, so what is optimization? Optimization problem is you have a target function and you want to find the local minimum or maximum of that target function. So in this case, so target function is quadratic polynomial of binary variables. That's why we have quadratic and binary. And sometimes when you want to find the optimization or solve optimization problem, there are constraints of that optimization process. For example, if you remember Lagrangian method. So you have hard target and you have constraint, and also convex problem, you have constraints. But in this case, you don't have any constraint except the target function. You just want to find the target function to be minimized. So that's why we have one constraint. There's no other thing that other than target function. And so here is a question. Okay, so once you have this quadratic binary polynomial, you want to find the local minimum using the quantum annealer. So for example, so let's think about this binary polynomial. So what's the degree? It's 2, right? And, well, okay, so therefore it's quadratic polynomial. So, and I also assume that x0, x1 are binary variables. So it's either 0 or 1, right? So let's say I want to find the minimum value of this function. What is the minimum? What's the minimum value of this polynomial p? 0, yes. When does it attain 0?
1, 0.
Yes, 1, 0 or 0, 1. So when x0, x1 are different, then it always have 0. So when x1 and x0 are equal, then it's 1. So p only has 0 and 1. I mean, it doesn't have to be always 0 and 1. The value can be larger than 1, but it just happens to be that way. And so there's reason why I introduced this type of polynomial. So as long as you have a degree 2 polynomial, you can set any function. But let's see. When you try to make a quadratic binary polynomial, let me just warn you that you don't want the value of p or value of function to be binary values, which means that you can expand this like this, right? Here, I'm assuming that x0, x1 are binary values, but I don't expect the whole operation is binary operation. If these were binary operations, x0, x1 plus x0, x1 is 2 times x0, x1. 2 is 0 in binary value, so it has to be disappeared. But we don't want that. I mean, we're not expecting that. So value of function is actually an integer. So it's 2 times x0, x1. So 2 is not 0 because we're not talking about binary operation. And minus x1 and x0 plus 1, right? And another thing I want to make emphasize is that, okay, so as I said, we want to implement this function into our QPU. I think I know how to do this, x0, x1, because now I want to make kind of electric current set up into the x0 row and x1 column. So it has to be the strength of electric current on these two, the section, this cross has to be twice stronger, as much as twice stronger than the normal one. And I also want to set the minus current on x1 and x0. So the question is, how can I set up that strength of coefficient minus 1s for x1 and x0? Because there's no simple single x1 or single x0. They always have to be, it comes in pairs. So in this case, when you think about x1, since it's binary values, it's x1 squared, right? And x0 is also x0 squared. So in fact, even though we talk about x1 and x0, we actually are thinking about square of them because it has the same value. So when you want to make minus x1, you want to make a minus 1 current into the section of x1 and x1 right here on the diagonal, right? So whenever you have a degree 1 terms, then you can do something on the diagonal sections here. So that's how it's done in the actual process. So in the MS bracket, you want to set the matrix, not a polynomial actually. So you want to set a matrix with coefficient of each terms to be entry of the matrix. So whenever you have this first degree term, then you want to do something on the diagonal part of the matrix. Right, so is that kind of clear? What is that? What's going on? So I want to do with a concrete problem. Okay, so this is kind of an overview, and I want to introduce how this quantum annealing problem is applied in solving concrete problems like graph coloring problem. And I'm not saying this is the only problem that quantum annealer can solve. There are actually many. And people, if you search for the application, you can see the traveling salesman problem is one of the main problem or objective problems that people want to solve using the quantum annealer. And okay, so let's start from this. So what is graph coloring problem? So what is graph? So graph is just a collection of vertex and edge. And when you say vertex and edge, you can say this is one-dimensional simplicial complex in a mathematical term. But also you can think this as there are finitely many vertices and there are some edge joining these vertices. So this is graph. And we're not so there are many types of graphs. Sometimes there are directed graph, because if you can think of the edge as somehow having a direction, and you can represent the direction with an arrow. So that's called directed graph. And sometimes you have more than two edges joining the same pair of vertices, and this is called multigraph. But we don't assume that. We don't assume there is a direction of each edge, and we don't assume there are more than one edge connecting these two vertices, so it's called simple graph. So it's undirected, single edge. And I'm not saying that every edge must be joined by every two vertices are joined by an edge. So you can have this kind of disjoint pairs, disjoint collection of graphs. And if you do have such a case, then you can actually make a problem a little bit smaller, because whatever you do on this subset of graph is same as doing it same in the whole, right? So if it's possible, we want to make it kind of connected graph, which means that every vertex is somehow connected to another vertex with path. So if it's not connected, as I said, the problem can be split into smaller problems. So you're actually dealing with the smaller ones. You want to solve it you want to go for the smaller one. And so the smallest problem that we can work on is work on connected simple graphs. And what is the coloring problem? So here, again, so the word coloring means that there are colors, and we set C to be the set of colors. The color, actually, you can think of as a color, but color can represent other things. For example, people usually put numbers as colors. So I want to say, instead of drawing a color, coloring a color, you can label a number on the vertex. And I can give you another example. So let's define the coloring problem first. So coloring means that there is a function that maps each vertex give a color. So C is a small c here, so it's a coloring map. And it sends every vertex into a color in the color set. So I'm not leaving out any vertex. Every vertex has to be colored. So for example, let's say I have a coloring set 1, 2, 3. Okay. So then it means I want to assign 1, 2, or 3 for each vertex. So I can say 1, 1, 2, 3. So that's one way I can color it. But coloring problem asks me another thing. So there are conditions such that if VW, which are vertices, lies in the edge set. So E is a collection of edge, and edge is a pair of 2 points. Right? So if VW is joined by an edge, so we call this pair an edge. If that's true, then CV, which means that the color colored in the vertex V must be different from the color colored in W. So that's the only condition of graph coloring problem. So think about this coloring. This vertex and this vertex are joined by an edge. I colored it the same color. So therefore, this is not graph coloring. So in order to do that, I have to change it to 3. I cannot change it to 2 because then I have a contradiction here. So graph coloring problem, there are many variations, and also people call coloring problems in different meaning. So this is one way of describing coloring problem. Sometimes people say coloring problem is finding the minimum number of colors that you can color the entire given graphs. So for example, if you have a graph like that, the minimum number of colors that you can color a graph, this graph, is 3. You cannot color with 2 colors, right? So it's called a chromatic number, and people want to find the minimum number of colors, and people want to find the statement or theorem that in what circumstance or what condition of graph you can color the entire graph with a certain number of colors. So our question is simple. Actually, you can probably make the question into something you can implement into quantum annealer. So question is how to use quantum annealer to solve graph coloring problem. This is our question. The graph coloring problem, again, in our class, meaning that finding this function, I want to find assignment of each vertex into some color that colors properly the entire graph. So we have to make somehow the graph coloring problem as an optimization problem, right? Because the quantum annealer is solving optimization. So, and also, in order to make it into an optimization problem, you have to make a target function, or sometimes called utility function. So how do you make the target function? So the first step is think about the simplest graph you can think of. Well, maybe simplest graph is just 1 point, but that's too simple. So let's say we have 2 points in the graph, and then these 2 points are joined by an edge. So then, how do you make the simplest graph to be transferred into optimization problem using the quadratic function like this? So here is graph V and W. Here's an edge joining these 2 vertices. And I want to have a minimum value of the function if the 2 vertices are colored in a different color. And it has to be a bigger number or not a minimum number if these 2 vertices are colored in the same color. Right? That's my objective here. So let's say xv and xw. So this vw is a vertex and xv, xw is the color colored in vertex V and W. Okay? So I'm assuming that these VW, XV, XW are 0 or 1, which means binary variables. And also there are 2 colors, only 2 colors, 0 or 1. Okay? So now I use this polynomial. So let's say PVW. So this is the polynomial only regarding about these 2 vertices, V and W. Let's define this polynomial as XV, XW plus 1 minus xv, 1 minus xw. So now it makes sense, right? It's a right proper polynomial. It's 0 when xv, xw are different. It's 1 when xv and xw are the same. No matter what the value is, I just want that, right? So let's say this is our actual graph, and this is our objective function. Let's say we put it into the quantum annealer and ask to find the minimum solution. So it probably give you one of 2, so 0, 1 or 1, 0. So you can take any solution, right? So there's no right solution here because both give the minimum value, so you can take any of them just as a solution. So now, the real life problem or the actual graph that you want to work on is not as simple as this, but you want to make a little bit complicated function. So how do you make it complicated? So let's generalize a little bit more. So instead of 0, 1 as a color, because there are only 2 colors if then, so I want to make a number of colors into bigger than 2. So how do you make that possible? How do you make number of colors increase? So everything must be binary variables. So your color must be also number. So in this case, you cannot use 2, 3, 4. It has to be represented by binary values. So every number has to be binary numbers. So therefore, you must have a number of digits of the numbers. So let's say I want to set 0, x, 3. Let's see. So let me write it this way properly. So x, 3, k, m minus 1. So there are 2 indices here. So for one vertex here, v is then for vertex v, and then m minus 1 is the place of digits here. So m minus first digits is x3 m minus 1 up to x3 0. So this is a binary representation of a number, and this number represents the color. So in this case, I can simply say that there are 2 to the power of m different colors I can draw into this vertex. And same for w. So here x, w, m minus 1 up to x, w, 0. Okay. So if I could color into the 2 to the m the different colors into v, I should color the same amount of number of colors into w. So I should have the same number of digits for the binary representation of the number as a color. So now, what I want is, I want the color on v and w to be different. So when does it differ? So let's say this is xv. So this is kind of a vector, so I put the vector notation here, and this is xw. Okay. So we want xv to be different from xw. So that means for at least one I from 0 to m minus 1, this x3i has to be different from xwi. That's the only condition we want. So we want that if this happens for at least one places in the binary representations of v and w, then the target function must have a minimum value, right? The same minimum value as long as this happens, right? But if it doesn't happen, which means that if these are the same all the way up to the last digit, then it shouldn't be the minimum value. It has to be different value. So basically, we also say that there are only 2 values possible in our polynomial, either minimum or not minimum, right? So how do you set up that function? So in that case, let's redefine our PVW as follows. How about this? Does it make sense? So what's the value of this function when the colors are different? So different color means at least one of the places of binary representation of those colors must be different, right? Let's say the ith place, the digits on ith place are different. Then if you're looking at the ith factor, so this means that you're multiplying these terms m times. So let's say ith factor here, this must be 0, I factor must be 0, if that's the case. Right? So then, if one of the factor is 0, it doesn't matter what other factors are, everything goes to 0. So P is 0 if xv is not the same as xw, and well, not 0, maybe 2 to the n, I don't know, but not 0 anyway. If xv is equals to xw. It really doesn't matter what the not 0 value is, because we're going for the minimum value. I mean, if you want to go for the maximum value, you can just take the negative everything here. But anyway, so now we found the proper function that colors the simplest graph consists of one edge and two vertices. So that's how do you make it into, how do you generalize to general function? General graph. So let's say we have VWU. What do you want to do? So we know how to take a function that has a minimum value when these two vertices are colored differently. We also want these two vertices colored differently, right? So we want the minimum value here, and we also want the minimum value. We want the target function to have a minimum value when it's colored properly. But if this is, so let's say this function that gives you the minimum proper coloring has a minimum value 0, then the target function that checks the proper coloring between these two vertices also has to have the minimum value equals to 0. So whenever these graphs are colored properly, you want the minimum value to be 0. So that's called Q as a target function that checks the proper coloring of the graph. And this must be the sum of all the polynomial that is the target function of each edge here. So in this case, I want to find PVW and then PWU and then add them together and call it a target function, because this is 0 when VW are colored properly, and this is 0 when the W and U are colored properly. So if I add them together, the minimum value is when this is minimum and that is minimum. And also, the minimum value of each polynomial are the same as 0, so that's not a problem. If they are different, if minimum values are different, then that's a problem. But we assume that the minimum is always 0. So it's not only 0, it's positive. Let's make correct here. So whenever you have VW connected by an edge, which means that this pair lies in the edge set of the graph, then you want to add this polynomial. Okay, so let's think about the example. So we have this example. Let's call it G. And let's try to make a polynomial here. And before you make a target function, you also have to decide how many digits in your color in the binary representation of a color. So let's assume that there is only one. So every color is a color, either 0 or 1. So I can set xv, xw, and xu as a color. So in this case, so PV is xv, xw plus 1 minus xv, 1 minus xw plus xw, xvu plus 1 minus xw, 1 minus xu. So let's expand this. So we have 2xv xw plus 2xu w xu and minus xv minus xw, but there's one more xw here, is 2xw minus xu, and then plus 1 plus 1 plus 2. Okay, so there's one more question. So we have constant term. We know how to deal with the degree 1 factor when you put it into quantum annealer, but how about the constant factor, constant term? Well, you can just ignore the constant term, because constant term doesn't, in fact, doesn't matter when you search for the minimum value. Well, it actually matters when you want to find what the minimum value is, but it doesn't matter if your searching is the solution to get the minimum value, right? Plus 2 is shifting the entire value by 2. Anyway, so this is our quadratic polynomials. How many variables are there? 3, yes. So you can make this polynomial into 3 by 3 matrix like this. Let's say V is 0, W is 1, and U is 2. So I'm just labeling these variables in orders. VW, so which means 0, 1 is 2. So it's 2, 2 here, off diagonal. So I'm taking 0th row and 0th column to be the first row and first column here. And WU, 1, 2, is also 2. And VV, so minus 1 here. And W, minus 2 here. And U, minus 1 here. And 0. This one is about VU. There is no VU, right? VU here. That's your matrix. That's your Kubo matrix in some sense, and then you put it into the quantum vanilla, and then it gives you the solution of xv, xw, xu. So in this case, there is only one solution. There's only one minimum value. So it's either 0, 1, 0. I mean, there are two solutions, right? Two types of solutions: 0, 1, 0, 1, 0, 0, 1. Right? So there are only two. So if you run this once, it gives you one solution, and if you run it twice and it gives you another solution, maybe it's the same solution as before, but if you keep running it, maybe about 50-50, you get two solutions. Now the question is, what if I have even more complicated graph and I had to use more number of digits in my binary representation of number colors? So think about the general shape. So maybe this case. So if we have, well, let's say 4 colors, what happens? Let's say what happens in this graph, or maybe not even this graph. But let's think about the simplest graph. And the quadratic polynomial is now I from 0 to 1. There are 2, and x v I x w I plus 1 minus x v I x w I, and then let's make it simpler. So x v0 to be x0, x v1 to be x1, x w0 to be x2, x w1 to be x3. So there are 4 variables. There are total 4 variables, and this is now x0, x2 plus 1 minus x0, 1 minus x2 times, now when xi is 1, x1, x3 plus 1 minus x1, 1 minus x3. So you can see that this is not a quadratic polynomial anymore. Well, let's expand a little bit here. So the maximum degree is 4. X degree, x0, x1, x2, x3. And let's see. Third degree could be coming from 1 to here. So x0, x1, x3, x1, x2, x3, and 1 to here. x0, x1, x2, and x0, x2, x3. So I think we have all 4 choose 3 cases, right? And something else follows, blah blah blah, right? So next part is okay, kind of. So the next part is kind of quadratic, right? Because that's the degree 2 parts. But the problem is we have degree 3 and degree 4 parts. We cannot put that into the quantum layer right away. So we have to do something. So we have to lower the degree of polynomial into 2. That's called the degree reduction. Now, so this is a simple idea. If you want to degree, so I don't want just degree to be lowered by 2. I want to preserve the value of the function. But it's not really possible. This is a quadratic polynomial. You cannot make, so it's a simple math. You cannot make the same graph of degree 4 polynomial as the same as graph of degree 2 polynomial. You cannot get the same function. You cannot get the same value. So our degree reduction is trying to make a new polynomial or new function to attain the same minimum at the same solution. Right? So degree reduction is finding a quadratic polynomial that has the same the minimum at the same point. So I'll tell you one example here, and then I'll give you the general formula. So think about the simple one, the x0, x1, x2. So since there is a minus sign, let's not forget minus here, minus x0, x1, x2. So this is equal to the minimum value of w, let's see, 2 minus x0 minus x1 minus x2. So I should say minimum here, but okay, so let me make a modification to here. The minimum same as minimum of minus x0, x1, x2. So this is the simplest degree reduction method maybe I can introduce. So let's think about what this means. So what is the minimum value of this? When does it get minimum? Right, its minimum is -1 when x0, x1, x2 are all 1, right? So the minimum is -1, and that happens when x1, x0, x1, x2 are 1, 1, 1. Okay, so let's focus on these parts. So I don't want the same minimum value of these two polynomials. All I want is the minimum on each side are attained at the same point. So this minimum is attained at 1, 1, 1. Let's see now, how about this? So we have a new variable, w is just another binary variable. It was not in here, but we had to add in order to make the same point to be minimum. So just think about this as a new polynomial of 4 variables and think about when this becomes minimum. So how can you make this as a minimum?
W is your
W is what?
Your minus.
W is also binary variable, so it has to be 0 or 1. W is always 0 or 1. So there are 2 cases, right? So when W is 0, then everything is 0. So that's the one possible minimum value. Let's assume that W is 1 now, and we have to search for whether we can make it into a negative number, even lower than 0. Right? So, and W is 1, we have to make this into negative value to make a minimum. So that's when we have 1, 1, 1, right? So this is the point where this right-hand side gets minimum. So you see, W is an auxiliary variable. It's a kind of a necessary, but it's not really important because W is not a part of the problem. W is just arbitrary, just addendum here. But what we want is, we want to have what's the value of x0 to x2. And when you make this polynomial, degree 3, into degree 2, so that you have to note that this is degree 2 polynomial, the minimum is attained at the same value as before, x0, x1, x2, all equals to 1, 1, 1, right? So therefore, now you can just find the minimum value of this polynomial. I mean, not the value. You have to find when this degree 2 polynomial attains its minimum, and then you only retrieve what is necessary here, and you can expect that this is the point where the degree 3 polynomial is minimum. So that's the idea of a degree reduction. And I'll tell you one more example. So we have the degree 4. Let's think about degree 4 reduction here. X0, x1, x2, x3, the minimum of this. So it's kind of a, yeah, well, let's think this way. So it's kind of, it's leading to say minimum is equal, because what I'm not really trying to say that the minimum is equal. It's actually the point where these two polynomial gets minimum is equal. Anyway, that's xi, xj, ij not equal, and plus d, so d in this case is 1, 1, 1, 1. Okay, so 1 is only one w here, w, and 3 minus 2 times xi. So let's think about this case. So when does this become minimum? I mean, what is the minimum value, of course? It's 0, right? So it becomes minimum if one of these 4 is 0, right? So there are many, 2 to the 4, 16 possible ways to choose the 0 and 1 for each variables, but there are only, except for 1, when there's 1, 1, 1, 1, everything is minimum 0, right? So let's see what that happens here. Okay, so I want to set up the table here. So let's see. Xi, xj, and then so this xi, the index is run from 0 to 3, so there are just x0, x1, x2, x3, all added up together. So this is actually counting the number of zeros. Do you know what I'm saying? No, sorry, it's a counting number of ones. Sorry. So if it's 0, means that there is no 1 in the list of x0 to x3. So I can say 1, 2, 3, 4, up to 4, right? No more, just 0 to 4. And how about this? So if there's no 1 in the list, what's gonna be this value? 0. And how about this? 0. How about this one? 1. Yes, because there are only 2 1s. That's only when we have multiplied them together to get 1 here. How about 3? 2, 3. Is it right? So how do you choose? How do you make a calculation here? So it's 4 choose 2, right? So you have to choose. The only way you can make non-zero value in this sum is you choose pair of 1s. There are 3 1s, so you have to choose 2 pair of 1s among 3. So it's a 3 choose 2. 3, okay? So how about this? What's the value? 4 choose 2. Okay, so 6, right? So you determine this value. So let's, okay, so let's call this here. Let's think about the value of this polynomial, left-hand side polynomial. Okay. What's the value of the left-hand side? 0. What's the value of the left-hand side in this case? 0. 0, 0, 1. Okay. So I want this, and so at least I don't care about what happens here, because I want the minimum value to be attained at the same case for the right hand side. So let's think about the right hand side, right here. So the formula is here. The first term is 0, and here we have 0. So all we have is 3W, right? In this case, 3W. When does it become 0? When is minimum? Is it when W is 0 or 1? 3W is minimum when W is 0, right? So the minimum value is 0. Okay, so think about this case now. So 0 plus W times 3 minus 2 times 1. So it's also W, 1W in this case, right? 1W is minimum when W is 0. Actually, it's 0 anyway. The minimum is 0. So now we have 2. So here, 2 plus, 1 here. 1 plus W times 3 minus 2 times 2. So I think I write it down here. 1 plus W times 3 minus 2 times 2. So it's 1 minus W. So now, when does it become minimum?
W is 1.
W is 1, and the minimum is 0, right? So let's think about the next case. So the polynomial is 3 minus W, 3 minus 2 times 3. So it's a 3 minus 3, is it close? This is closer. So 3W. When is minimum? When is it minimum? Yeah, W is 1, right? Then it's 0. So now let's look at this one. So far we got the same minimum, right? And we had the same xi's, right? We have the same xi's. And let's look at the last one. We have 6 plus W, 3 minus 2 times 4. So 3 minus 8 minus 5. Minus 5W. So when is minimum? 1. It's actually when W is 1, then the minimum is 1. So you get actually the same minimum. So yeah, we really want to have the same minimum, but also we want to get the same minimum at the same xi's. So we have the same xi when we have this, not exactly the same xi, but we have the same sum of these xi's and xi times xj. When xi's are the same thing. And you can see that on the right hand side, you get the same minimum value for each cases. So except for the last one. So you can say finding the minimum of this polynomial is same as finding minimum here. But this one is quadratic. There's no degree 3 or more. Everything is degree 1. 3W is degree 1. And WXI is another degree 2 polynomial terms, and degree 2. Yes, so we have another auxiliary variables. W is not in the original polynomial, but we need that in order to make degree less than or equal to 2. So here I'll give you the formula. So there are 2 types of formula. So what happens is, so far I only decided, not here, where is I raised. So for each monomial, so this is monomial. So monomial means it's terms on each term in the polynomial. I can reduce the degree of monomials, and I have to decide whether the coefficient of that monomial in the polynomial is either negative or positive. So if it's negative, this is the Friedman formula, and this is same as minimum of this. So we need only one auxiliary variable W to make this polynomial. So d is the degree, and that's bigger than or equal to 3. So it's equal to that quadratic polynomial. And if it's the coefficient is positive, then you can make it into you have to split 2 cases. So this is the case of, so I made an index 1 from 0. So this is the case when your degree is even, okay, not odd. So even though we have d 2d plus 1, which is odd, the number of factors are even, and because we're starting from 0. And xj is equal to xi, xj, where ij is not the same thing. And, oh, okay, so, yeah, everything has to be put into the minimum, so let me write it down again. The minimum ij, xi, xj, and then I from 0 to d minus 1. Let's see, 4i plus 3wi and minus 2. Sorry, so okay, so it has to be big sum here. Sorry, plus big I from 0 to d minus 1 wi times 4i plus 3 minus 2 times j from 0 to 2d minus 1 xj. That's even case, so this is even degree. And the odd degree is a bit more complicated. J 0 2d xj equal I j xi xj. Sorry, forgot to put minimum here. Minimum I j xi xj plus I from 0 to d minus 2 wi 4i plus 3 minus 2 xj j from 0 to 2d. So this one I made a mistake here. It's a 2d plus 1. And that's one thing. And then plus w d minus 1 2d minus 1 minus xj from j from 0 to 2d. Okay, so complicated, but if you understand what's going on inside, it's really simple. It's very simple. So it's a side note. I made a research 2 years ago with a high school student how to generalize these formula. So these ones are the degree reduction on the monomials, right? So each monomial have at least one auxiliary variables. So here we only need one, but in this case, how many auxiliary variables you need? You need the auxiliary variables because wi, where I is the index of w, is running from 0 to d minus 1. So there are the more variables to take care with when you have the monomial degree reduction. And also here you have d. So d minus 1 up to from w0 to wd minus 1. But when I do the research with the high school student, so this formula actually comes from simple observation of arithmetic progression, and then we could make it into general formula applying to the symmetric polynomial, not simple. So monomial is one of the one of the special case of symmetric polynomial. And when you do the degree reduction on the symmetric polynomial, you could reduce the number of auxiliary variables almost up to 40%. So having less variables in your quadratic polynomial means that you could make your question, you can make a problem even larger to implement it to quantum linear, so it's probably better. So anyway, the idea is simple, that's what I want to say. And yes?
Is there any name for this?
This one is also Ishikawa.
Ishikawa.
Yeah, so Ishikawa too. And it's very interesting, and when I just looked at this one, so these two formulas, it seems very, it seems very elementary, but Ishikawa is discovered early 2000, and then, Friedman is early 2000, Ishikawa is like 2010-ish, or something like that. So, well, it's so simple. This formula seems complicated, but the idea is very simple. So I was wondering why they are not taking research into this more. So anyway, if you're interested, you can just do it. I think you can do it, but there are many problems you can even tackle in this quantum business. So anyway, so what I want to conclude here is, so remember the polynomial that polynomial associated to the graph coloring problem. There are many monomials in the quadratic polynomial. So I think there were 5. So when you use the degree reduction on monomial, you have to take the degree reduction on each monomial. So for each monomial, you put it into a different way in quadratic polynomial, and then you put that everything into one big quadratic polynomial. And also, when you transform monomial into quadratic polynomial, the auxiliary variables are supposedly the new ones. They're all different. So these W and these WI, they are different. This WI and this WI are all different. So there are way more auxiliary variables than the actual variable xi's when you do the degree reduction in general. But the quantum quantum annealer will try to show you the solution, the minimum solution, including the values in xi's, but you have to get rid of the information of wi, just retrieve what is necessary here, then that gets you the solution. So once you solve graph coloring problem with this idea, what it gives you is the map, how to color each vertex with a certain color, right? And you can go a little bit further from here, and this is just an idea that what if you want to find the minimum number of colors you can color the graph? So how do you solve this problem? Or maybe you have to set up different target function. Then you can find the exact number. But this problem, this settings, only requires 2 to the power of number of colors. So either 2, 4, 8, 16 colors to be colored in the graph. So you cannot fine-tune the number of colors between these powers of 2. So let's say you use the 16 number of colors to color the graph. You don't know whether it's 7 or 8 or 9, 10, 11, which is the minimum number of colors. You have to try again and again until you actually found, okay, maybe I found 10 number of colors to be colored, but not 9 anymore. Then maybe the 10 is the minimum number of colors, and that's the only way you can do it. But maybe if you change the target function to find the actual number of colors to be minimized, then probably you can solve a different graph coloring problem with the quantum annealer. I haven't seen that kind of target function yet. Anyway, that's the idea. So tomorrow maybe I move to another topic on quantum error correction.